So I'd like to thank the meeting organizer for their very nice invitation for me to have this opportunity to present this work. This is mainly on the materials side, but certainly, my work is my group is also work on the devices. In addition to myself, I have two co-authors. Qiming ZHANG is a postdoc scholar now at Penn State, and Professor Xiaozi Chen is at Shanghai Jiaotong University. So we'll talk about basically the materials related to ferroelectrics, and you will see there could have a lot of potential for wearable application. And again, there are already some applications that are used in the wearable devices and systems. So what is ferroelectric material? I will use the next slide to explain a little bit. Basically, a ferroelectric material are multifunctional. As illustrated, this is just one example. They have many cross-coupling phenomena. In here, you could look into between the electric and the elastic, electric thermal, electromagnetic, electro-optic. And also, they also have many cross-coupling between other variables. So you can see they have a very, very rich performance parameters. And here are some examples which we have been involved in the research, including electromechanical actuator sensors. And that's what we'll be discussing in this talk, electrocaloric effect and EC solid state cooling. And also transducer for imaging and for magnetic, for non-destructive evaluation. And there's a long list here. Okay, so it's a very interesting material, and it has been investigated very widely. And the device market for this material is on the worldwide about $50 billion. So it's very large market for that application. So the material which I'm going to discuss in this talk is a PVDF based ferroelectric polymer. So what is ferroelectrics? Basically is a material when you apply electric field, you will see something called this polarizing hysteresis. This can happen in the room temperature, can happen high temperature, can happen low temperature. For the PVDF, this polarizing hysteresis group, you will see it below temperature, about below 150 degrees C. So the material is very simple. It has a fluorine and hydrogen, very simple structure. So even before we use them for active materials, they are very widely used in plastic products and also paints. So it's used for many, many years. So it was in 1969, Kawai from Japan, they discovered relatively large piezoelectric activity in PVDF. That's over, but really the whole research. This is really a breakthrough work. And it took another 10 years for this PVDF TIFE polymer developed. As reported, for example, in this 1983 science paper by Lavinger. So it basically expands this VDF to a TIFE. This has a little bit larger size. There's a little bit larger size. And also its dipole is half of the VDF. But even with that, the performance, this PVDF TIFE copolymer is better actually than PVDF, and therefore it greatly expand the application range of this material, including in many wearable devices, if you look into the literature. For example, I just listened, what the previous speaker talked about energy harvesting. So even at that time, in 1989, this is a very popular science journal in the United States, in the Science News. It proposed that by combined PVDF TIFE copolymer, for example, you put it in the ocean, and then unlimited electric mechanical energy, you could generate electric power from the sea, right? So that's basically something we call green energy. But so the question is, can this be a reality? The answer is, there are many research have been done in the past 40 years, but it's still not a reality yet. So one of the fundamental reasons is the material has the piezoelectricity. Although PVDF TIFE is really the best ferroelectric and piezoelectric material in the market, but their piezoelectric electromechanical coupling is still much below, for example, the piezo ceramics. For example, the piezo coefficients of ceramic is about 20 times higher than a polymer, right? This means, with the same applied electric field, the strength generated in the polymer is 20 times smaller than the ceramic. And also the electromechanical coupling in the ceramic, for example, with K33 is about 3 to 4 times higher than the polymer. And this energy conversion efficiency is proportional to the square of this case. This means the polymer, the efficiency is about 10 times smaller than the ceramic. That's why, even after many years of research, basically, no practical device, you can reach the performance which is commercially viable. Okay. And also, when for many energy harvest application and other application, one like to have a high actually the strength, but as you can see here, the strength generated by this by PVDF TFE is less than 0.5%. Okay, so this is not good enough for many applications. Even also in the wearable, many sensors are used, but on the actuator side, the use is very limited. On energy harvesting, basically, it's mainly for the demo purpose, and no practical device have been used. Okay. So we are actually at Penn State, we're constantly visited by many companies, and they ask us questions: can you develop new material which can be better than the PVDF TFE? So it took us about 20 years. So it is in about 1998. We found that by expanding this polymer from the copolymer into terpolymer, this basically CFE, which is a little bit larger than the VDF TFE, we can convert this material into something called relaxor. Basically, it has a very large polarization, large and broad dilute constant peak, and around this peak, your polarization is very much polarization hysteresis. It is basically there's no hysteresis, right? So this means this is totally new class of material, and several papers we published in a few journals. And also, what happened here is that what's interesting is this material actually at that time was the first polymer that can, an odd piezoelectric ferroelectric material generate such a large electroactuation, which is more than 7%. And so also different from many polymer-based, actually the material, for example, if you heard something about the dielectric elastomer, their modulus is only 1 megapascal. It has a relatively high elastic modulus, between 200 megapascal to 1 gigapascal. So they very much bridge very nicely between the hard PZT ferroelectric ceramics and a very soft dielectric device. And such a large change of the largest strength is really due to reversible conformation change between the polar ferroelectric polar conformation and a non-polar conformation. You can see there's a large dimension change when you go from this non-polar to polar phase. Okay. So it's, and also, the response is pretty quick. It's about 100 kilohertz. So it's very encouraging. So here is two examples you can see here. So this is a thin film bimuff. It's about 2 centimeters long, about 40 microns thick. And you can see applied electric field, you can generate shape change from this flat into very small curved ones. And also, you can see this artificial muscle. Basically, it's a butterfly. And if you can control the shape of the fly, actually, you could make them into, for example, into electroactive polymer vehicles, right? So what's good about this material is this terpolymer is commercially available. You can buy them from Arkema Piezo-Tech. So that's so many people are buying it. And also the terpolymer thin film actuators and haptic devices, they are commercially available from Novasentis Inc. So you could also buy them there. And also the multi-layer thin film terpolymer devices for different applications, you can collaborate with polymer technology. Also, they can produce them. So this is very much available material, and for various haptic applications, there are various venues that you can obtain them. Okay. So this is a video provided by Novasentis. Actually, a few days ago, I asked him, I said, well, where your polymer thin film actuator used? So he said, how about take a look at this haptic device glove, and this basically you can see this is a glove, and the thin film haptic actuator embedded at the different junctions of this fingers, and it can show you the shape of your finger, and also where do you touch it. You can give you the voice feedback. So it's a very nice feature, for augmented reality and virtual reality devices. Okay. So also, for example, Samsung, they used this thin film actuator to develop the micro pump, and this is a very nice device, very small size, and very thin. It's about a few millimeter thickness. And when this thin film actuator change shape from flat one to the bended ones, it generates fluid change volume, and it change the focal length of this fluid device. And this really can form autofocusing for example, use for cell phone cameras. So I still investigate this one here, and the material, you can drive it at 40 watts. So this means you could even use them for haptic devices, and also they are very fast speed response. Right? So those are just some device examples of those two polymer thin film actuators. But also through those device works, we also get a lot of feedback, and a lot of people ask us, well, basically what they ask us is, although this two polymer, you get better than the PVDF TIP copolymer. For example, PVDF TIP copolymer, the piezoelectric coefficient is about 60. Now we can get 400, but need a high electric field, 100 megawatts per meter. And also we increase strength about 10 times. Again, it also need high voltage, and also the electromechanical coupling also occur at high voltage, right? So, from the device work, what they told us is, the device can only be operated at below 60 megawatts per meter if you want to use them for a long time, right? So, we are asked by various end users, can large actuation generate at a low electric field, less than 60 megawatts per meter? And also, can high electromechanical coupling factor be realized at low field? They say, you can get 0.5 coupling factor. Can you get even high? For that, can we get much better than the PZT? Okay. So to look into this one, actually, we need to look at fundamentals about polarizing response in ferroelectric material, right? For example, if we apply electric field in dielectrics, you will change dipole moment. So this response could be from, for example, for the electronic, from without electric field to electric field, atomic, dipoles, and also from space charge. Also in ferroelectric, if you look into ferroelectrics, there are many different types of ferroelectric polarizing response. And what I find is most of the times when people do research, they never ask this fundamental question. That's why we miss this for so many years, right? For example, in a ferroelectric, in ceramic or polymer with those ferroelectric domains, if we flip this dipoles, further flip this domain, change the direction 180 degrees from here to there, right? Basically, you increase polarizing quite a lot, but there's no electromechanical response. So basically, for example, if we have this pencil, if you flip it 180 degrees, the shape is the same, right? So when we work on those active materials, when I look in the literature, not many people ask the question: how can we, for example, how can we generate desired polarization while reduce or eliminate undesired polarizations? Because for example, in here we talk about electromechanical, but in some other cases, for other applications, so can we design the scheme, the general approach, so that we could, to some extent, selectively choose polarization which we want, and we're also surprised the ones we do not want, right? So it's certainly, this is good. This is interesting question, but also it will take a while for us to find an answer. And it was last year we found that, by convert small amount of CFE monomer into this double bond, we call it FA bond, okay? We basically could reduce the barrier for the conformation, for example, this is the trans-gauge, trans-spiral bond, trans-gauge prime for this polymer monomer unit. This is the CFE, and this is another side, this black curve. You see the barrier is relatively high. Now, if you convert the CFE into the double bond called FA, you can see this red curve, basically the barriers for this dipole bond to rotate, barrier is much smaller. So this really suggests, this approach could be a very attractive approach, and this means we need to convert expanded polymer from the terpolymer to the touch polymer, right? So once we think about this, actually, it is really not so hard. Basically, what you see is, we find if we convert about 2% more of CF into the double bond, you can generate strength, for example, at 50 megawatts per meter, we can generate strength about 4 times higher than the terpolymer. This is very surprising. You just need to change very small amount of defects. You can generate such a large actuation. And also this is the loop, electrostrictive response. And also, this is basically the electrostrictive material. So how can we also generate piezoelectric response in electrostrictive material? So the one easy way to do it is to put a DC bias field on. So that's illustrated here. So this is the strain response with electric field. But if we put a small DC bias field here, and you can see applied electric field can induce linear response, this is the piezoelectric response. So this actually has been widely used in some other, for example, magnetostrictive material, and also for a lot of BAM devices that basically operate as this principle. Okay. So it's very simple. For this touch polymer, we find we apply, for example, DC bias field of 30 megawatts per meter or 40 megawatts per meter. We can generate, for example, piezoelectric coefficients about 1,000, right? The PVDF TIFE is about 30 to 40. This is 1,000. It's many, many times larger than that. And in addition, the electromechanical coupling can reach about 88%, which is also much higher than ceramic, which is a PZT ceramic, which is about 75%. So this is the summary. For example, this is the material which we are talking about right now. And this is the best ceramic material with piezo coefficient about 700, and the coupling is about 0.75%. And those are all other early works on PVDF based material. Okay, that effect are pretty small. So also by using a different DC bias field, this is a numeric. This basic table show you the numbers, right, for the PVDF TFE. This D3 is about 33 and coupling factor about 23%. Now this new material you can get about 1,088%. And also this effect, just show you certainly although at high bias field you can get large response, but even with a reduced bias field, your response is still pretty high. I think I do not show you the data, 10 megawatts per meter, which is still more in this composite, still more than 1,000, and the coupling is still about 70%. So basically, this new class material, this is still the beginning of the last step. We believe we can improve this performance, can be much better, increase piezoelectric coefficients, and the question is, can we even make this one 100%? And also, can we generate this effect without a DC bias, right? So those are all for future research. But anyway, even with this result, it's already very exciting. And we also work very closely with the theoretic group, because we find they can provide a lot of insight and also give us a lot of future directions. So this group, Jerry Benhoek at the NC State, that really excellent, in the computer simulation for polymer system. So they basically carry out molecular dynamic simulation and density function calculation on the relaxor polymer with and without this FA bond, right? For example, this is the PVDF copolymer without in the 3-1 helix. This basically is a polymer conformation, which is random without polarization, without net polarization. And you can see, and this is the one with the FA bond. And when we apply electric field, we can convert this 3-1 helix in a simulation into all trans conformation. You can see the interchange space is reduced. That means the intersecting side has become thinner, and along the polymer chain direction, it becomes longer. This is the actuation strength. And so for both PVDF TFE and PVTF with FA, you can see, you can realize this transition between non-polar and polar conformation. But what's the difference here is with the electric field, as I said, the double bonded FA reduced the barrier for the transition between different conformations. So you can see here, with semi-electric field, with a polymer without FA, you only generate transformation between, for example, at this electric field, from the non-polar bond to polar bond, only about 16%. And with FA, you can immediately raise it to 42%. And if you convert this into a strand, that's about, for the pure PVDF TFE, it's about 1.3%. And with FA, with only one, actually in the calculation, there's only 1% more of FA, the strand can be about 3 times more. So this means with very small amount of FA, the double bond, we can generate much higher electromechanical response. From theoretic side, prove what we have done experimentally. And because in ferroelectric material, in general strand, they are, you can consider them as electrostriction, basically is proportional to the square of the polarization. So this is a measure of how effective the polarization can generate strand. The coefficient is called Q33. So if we look at the touch polymer, this number is about 10 times higher than what happened in a PVDF TFE copolymer. So our experiment result and also theoretical calculation really verify that this class of material, this approach, really could generate a very high electroactuation with high electromechanical coupling. So we're still working with this group and see on other conformations and other compositions, and hope for them in the future I can give you better results. Okay, so this basically this we have this new touch polymer which is much better than the commercial two polymer, and that two polymer has already been relatively widely used in various haptic devices, in various actuator devices. Right? Okay. So now let me switch it here and talk about electrocaloric effect. And our early purpose is really to address something called global warming, because refrigeration system is really in Hong Kong. Actually, everybody use air conditioner, right? But the refrigerant in those air conditioners, they actually are the major cause of global warming. Okay, and also in the US, I do not know what's happening in Hong Kong. Right? This cooling really consume about 30% electricity. So if one could develop a new alternative cooling technology which can be more energy efficient, right? Then this can also address the issue of the energy efficiency. So this is to some surprise, that the ferroelectric effect has been studied for many decades. Okay, as soon as people know the ferroelectric material, but this reverse effect actually had not been studied until very late, as I will show you in the next slide, right? So let me just define briefly what is something called electrocaloric effect. Basically, in a dipole material, if you have dipoles, right, apply electric field, we could align dipole, and in this process, this material will eject heat, just like we compress air, it will become hot. Now, if you can keep this one at the room temperature, and when you reduce the electric field to 0, actually the dipole will become disordered, and in this process, actually the material will become cold, and it will absorb heat from external systems. So electrocaloric effect basically is quantified by the adiabatic temp change delta T. This means when you apply electric field and the bad condition, how many temperature can change, how many degree. Also isothermal entropy change of delta S of dielectric material. Okay, so this has several nice features. Basically, it generates 0 greenhouse gas. That's good. And it is compressor free, so there's no noise. And this actually can be scaled to any size and load capability. So those are actually very much similar to the thermoelectric cooling. But what's interesting is, many modern results indicate that with high performance EC material, the EC cooling can reach high efficiency. Actually, efficiency can be assessed. I will show you from the simulation result of the United technology, which can be at least 25% better than vapor compression system. In addition, those EC devices, you could use them for localized cooling, and this will further improve the energy efficiency. Localized cooling, for example, for wearable cooling. Okay. So I think we don't. So actually, the EC we are not the first one to study EC. So it has been, for example, the first report of electrocaloric study is in 1930. So it's nearly 1 century now, and in the ensuing years, people find that at the room temperature you can get adiabatic temp change less than about 2 Kelvin, 2 degree, and at high temperature it's about 2.5 Kelvin. And all are in the ceramics, right? So again, we ask the question: can large EC be generated in ferroelectric material? That's first fundamental question, because all those things are very small, right? Okay. So answer actually is not so hard, because we did some theoretical analysis with a group from Slovenia. Basically, the entropy change in this electrocaloric material certainly is proportional to the polarizing square. This is why we use ferroelectric material. But also it's related to its randomness of the material. This omega is the number of possible polar state. Basically, it's a measure of how random your polarization can be. Okay, it's a number state. And also inversely proportional to this called C. This is Curie-Weiss constant. Basically, this is directly related to the polar correlation in the material. Okay, so when we look into the material system, actually we feel when we really should look at the polymers, because what happens in the polymer is much more random than the ceramic. And if you look at dielectric constant, the polymer dielectric constant, even we get the relaxor, is about 50 compared with the ceramic, which most of the times could be several thousand, right? So this means both this omega for polymer can be large, and the C for the polymer can be small, and in addition, so that's what I thought, right? So we basically, for example, look at the PVDF based polymer. Actually, if once we thought about this, it's very simple. You look at this material, you can see between the ferroelectric and the parallel transition. So the heat of transition is 24.3 joule per gram, which is pretty large, Okay. And if you convert this one into the adiabatic temp change, this means you actually, even at this transition, you can get 20 Kelvin temp change, electrocaloric. But this will be at high temperature. So what happens is, if we can convert it into relaxor material, because you have in the relaxor we have something called local random fields, they can lead to even larger number of local states beyond that allowed in the normal ferroelectric. And so the relaxor, because we have defects that they can further reduce the coupling between the polarizing, and they can further enhance the electrical. So this, once we thought about this, actually it's not so hard to show that this is actually, it's about 10 years ago, we showed that in the relaxor, which is produced by the high energy irradiation, we can get about 20 Kelvin temperature change, temperature. And also polymer, you can get more than 16. But my colleague, they measured this one to 250 megawatts per meter, and you can see actually that temperature change can be about 40 Kelvin. So basically, indeed, in this relaxor ferroelectric polymer, you can get a very large electrocaloric effect. Okay. So here are some of a summary of the state of art of electrocaloric material, which have been studied in many years after 2008. And you can see if you look at literature, there's a lot of report of bigger numbers, but many of those values are not so convincing. So those are the EC values that directly measure. You can see the temperature change is 20 Kelvin, 15, and as I said, there's a composites which can get about 40 Kelvin. So basically, this table shows that EC material at the temperature change less than 20 Kelvin in polymers and 5.5 Kelvin in ceramics really has been developed. So with this value, actually, people could work on many EC devices. So here are some examples. Let me just skip this one. Basically, all those EC cooling devices, they work on some kind of regenerative cycle, and this means using this cycle, the temperature lift between hard and cold end and can be larger than the delta TEC. So this means, if the delta TC is 15 degrees, you say we could get the cooling 50 Kelvin, right? Okay, so the question is, can we do that? Okay, so we did a very simple study. This is in 2013 and 2014 for the EC polymers, and we call it flat panel air conditioner. Basically, this is a very flat one. Basically, you have a counter-rotating EC discs, one in one direction, another one clock direction. And the thickness could be about, I have pictures, but I do not show it here. It could be about 1 centimeter, and the size could be 10 centimeters. And that's the cooling side, it's half centimeter. But what happened here is we find, the maximum temperature span between hard and cold end is only about 6.5 Kelvin. At that time, this is really the highest in all these devices. And also United Technology, which is a company in the United States, and also Carrier, this is the major HVAC company, produce all those air conditioner refrigerators in the United States. And they did a study of using EC polymer. And in this case, they basically put EC polymer film in a stack and directly use air to exchange the heat and to generate a regenerative cooling cycle. This is a device configuration. This is hard side, cold side, here is the EC chamber. And they made a device with a temperature lift about 8.4 Kelvin. And they also carry out a simulation which shows that with a high EC performance, for example, if delta T can be 7 or 8 Kelvin, the device, EC cooling device can have a 25% improvement in efficiency compared with the wafer compression cooler. So those are very encouraging results. Okay, but still the temperature lift is not that great. And also, for example, a team from UCLA and SI, they developed a kind of flexible EC cooling device, and they publish in Science. And basically, this is the EC film, polymer film, and when it becomes cold, it goes to the cold side. Now, when it becomes hot, it goes to hard side, eject heat. And when it becomes cold, it goes to cold side to absorb heat. Basically, in this way, you pump heat between cold and hot end. So they demonstrate about 8 degree cooling of a lithium-ion battery. And also they demonstrate a 8.7 Kelvin temperature lift in a cascade EC cooling. Okay, so those are the results here. So all those results, actually, there's some other EC cooling device on the ceramics. They're quite exciting, but overall, their performance is really not ready for practical device application. But then you say, why? We already have such a high delta T, delta S for the materials, why the device is still not that good. Okay. The reason is very simple, because in all those practical devices, we have to look at electric breakdown, right? Okay. So when we do the measurement, when we publish paper in the university levels, usually we measure the performance and at the highest electric field we can measure. Okay, let's say in this case, we put 150 megawatts per meter, we can get 15 degrees in the top. But in practical device, the electric field you can apply really should be at least 25% of that breakdown field. So this so that you can have a reliable device operation. So in this case, for the two polymers, this means you can only work at 60 megawatts per meter. And this field, the temperature changes are only 3 Kelvin. Okay. And also due to various parasitic losses, if you have a device, you have enclosed and many other things, right? So with 3 Kelvin, you have a lot of those EC effect. You have to overcome those parasitic loss. So a lot of system modeling also shows that in not for the EC cooling device, which can be competitive with the vapor compression cycle, you have to temperature change must be higher than 5 Kelvin. Okay. So you can see in all the EC cooling devices, actually the temperature change in the device is about 2 to 3 Kelvin. So that's one of the reasons why the performance is not so good. So the question is, can we get the large electrical effect, right? So now I do not have time to go give you a lot of details, but basically this is another case. We expanded from PVDF TIF2 polymer to the touch polymer. We can generate the cooling from 3 Kelvin, here 60 megawatt per meter, to more than 10 Kelvin. Very simple, right? Okay. And also using modern results, which published in the Science in 2020. This is for EC temperature change about 5 Kelvin. But now if we get 10 Kelvin, you can see actually the performance can be very impressive. For example, if we want to get 20 degree temperature left between hot and cold air, we can generate cooling very hot, about more than 5,000 watts per kilogram EC material. Okay, so this is the result we just published with Shells in Nature last year. Okay, and also in addition, we find by using a ferroelectric polymer composites, actually you can get this large EC at much low electric field. In this case, for example, you just need about 1 megawatts per meter. This means 1 watt per micron. So if you make 5 micron polymer film, this means you can just use 5 watts to generate this electric field, and the temperature change can be about more than 30 Kelvin. So what happened here is this is still not practical because this happened at 80 degrees C. So we still quite a lot of work to do in moving to room temperature. But anyway, this just shows you there's a lot of potential in a polymer-based system to generate large electrocaloric effect. Okay. So let me summarize. So basically, here I only show you the materials. I do not show you many detailed design of EC cooling device because with such a material, actually you could generate many device configurations. So basically, I demonstrate to you, in ferroelectrics, which is a multi-function material, right? You could use defects to markedly enhance the performance, enhance the policy response. So I just give you an example in the polymers. And in here, I just show you, you just convert 1 or 2 more % of CFE into the FA. In this polymer, PVDF, TIFE, CFE, we could generate piezoelectric constant and electromechanical coupling much higher than that in the PZT. And also, those materials also give you a very large temperature change at 60 megawatt per meter, which is voltage you can use reliably in a device. And we also show you even new polymer composites, even at very low electric field, you can generate very large temperature swing. So this result really show the promise of the ferroelectric polymers in generate high electromechanical and high electrocaloric effect at low fields. which really could lead to high performance wearable devices. Okay. So I'd like to thank you for your. This photo is the Material Research Institute. My lab and my office is in this building. So if you go outside, look at this building, this is what you see, because in the US, we are in the evening. So this is the photo I will share with you. Okay, thank you.
Professor Zhang, nice to meet you again. Here is Feng Yan from PolyU.
Okay.
Feng.
Yeah, yes. Thank you for your invitation for me to present this talk.
Thank you for accepting our invitation. It's a very nice talk. Thank you. So I'm very interested in your teacher polymer. So she's a very good property, particularly for this dielectric constant and the electrocaloric effect. So I have two short questions. One is, how about the lifetime of your teacher polymer for this electrocaloric application? And second one is, how to process the polymer to get a thin film, and so we can integrate into some other devices like transistors as a dielectric, which we have very thin film. So is it possible to get a very thin film by solution process?
Actually, we did a lifetime test. If you look at that's a Nature paper, and those even after 1 million cycles, it's a very brave experiment, right, for the student. And there's no issue of the fatigue, even at the 60 megawatts per meter. So it's very reliable. As I said, for device, we really need to work at a low electric field. And also, those polymers are very easy to processing. We actually have a paper published in using those PVDF polymer for as a gate dielectric for transistor, for thin film transistor in applied physical lab a few years ago. So yes, we're actually a little bit too busy. We really do not have time to look into a lot of device details. But yes, you could use easily solution test method, put on the very thin film. It could be as thin as 50 nanometer, if you like. Okay. And really the performance just like the bulk material using solution test. Okay.
Okay. Thank you, Professor Zhang.